We are now going to run a simulation. We're going to put a satellite right here. You give it an initial velocity in approximately this direction, an initial velocity of 5,000 meters per second. Now recall that low Earth orbit requires a velocity of about 8,000 meters per second. This is a little further out, maybe 5,000 meters per second will be sufficient, provided we give it the right direction. I gave it a direction about here. Maybe I should have given it a direction more like this, but let's just see what we get. Okay, we see the satellite beginning to move. Actually, it's getting kind of dangerous. It just crashed into the Earth. Now let's say that the Earth wasn't really as big as it is. Let's say the Earth had been shrunk down into a small ball. Then the object could continue to orbit that small ball, assuming the Earth maintains its mass. The object will follow an elliptical orbit around that mass. Now this orbit continues around. If the simulation is perfect, the orbit will close. Now this simulation is running on a very slow computer, and it wouldn't run at a reasonable speed if we used a time interval short enough to make it really good. I think you can see that this thing's going to come out here, and by the time it closes up, it's not going to quite close up at the same point. That's just a fault of the simulation. On a faster computer, we can of course run the simulation with a smaller time interval, and it won't have this effect. That's not what really happens. The orbit really does close for an actual object. But this gives a reasonable approximation of what happens. And we can see that at each point the object is being accelerated toward the center of the Earth by the fact that its motion curves in toward the center of the Earth. We can also see, if we watch carefully, especially in a faster simulation, that the object goes a lot faster when it's in here because it's losing potential energy as it approaches the planet. Again, assuming the Earth has been shrunk to maybe 1/10 of its radius, so we can actually orbit it. So, right here the object is moving very slowly because it's lost most of its potential energy. It's moving out against the pull of the Earth's gravitational field. The gravitational field is doing work on the object. It's losing potential energy. If it was allowed to continue back in, though, it would fall and lose, I'm not sure I said that right, it's losing kinetic energy as a result of the fact that the Earth is pulling it back. As it falls in, it loses potential energy. Its potential energy goes to a lower state, meaning its kinetic energy speeds up. And by energy considerations, we can see what happens. The actual orbit will be slow here, and then it'll gradually begin to speed up, and it'll go around here pretty fast, and then it'll come out here and slow down. Okay, out here at a maximum potential energy, it's as far away as it can get, and then it starts losing potential energy and gaining kinetic. Down here it's moving as fast as it'll go because its potential energy is at a minimum, and then it loses potential energy again. It gains potential energy and loses kinetic energy as it moves out to its far point.